devais résumer la bibranche avec vous aujourd'hui, je dirais que c'est d'abord des rencontres. Des rencontres entre étudiants appartenant à différents laboratoires, différentes entreprises, mais aussi avec des chercheurs venant du monde entier. Nous accueillons tous les étudiants appartenant au domaine de l'électronique, au sens large. Nous donnons la possibilité à ces étudiants membres de créer leur réseau professionnel dans des domaines qui leur tiennent à cœur. Être membre bibranche, et donc membre I3E par extension, cela vous donne beaucoup d'avantages. Notamment, vous aurez accès à une grande librairie d'articles de conférences en électronique, mais aussi à l'actualité des dernières technologies et aux événements organisés par les entreprises de pointe. Mais avant tout, cela vous permet de faire partie d'une des plus grandes communautés scientifiques mondiales. Et tout cela pour seulement $20. Sur le campus bordelais, on organise des événements à peu près tous les mois, sur place ou sous forme de virtual event, au cours desquels on a des invités tels que des chercheurs. Mais on permet aussi aux étudiants du campus bordelais de transformer leur projet d'études en projet I3E, en ayant un soutien financier, et nous les accompagnons aussi dans l'écriture d'articles scientifiques afin qu'ils aillent en conférence par la suite.
Être à la bibranche, c'est faire partie d'une équipe dynamique et soudée pour promouvoir la science.
Pour moi, la bibranche, c'est l'occasion et l'opportunité de changer son quotidien d'étudiant. C'est l'occasion d'organiser tout plein de choses, des séminaires, des journées thématiques ou encore des concours technologiques autour de divers sujets scientifiques.
Rejoins la bibranche.
La bibranche.
Donc rejoignez tous la bibranche.
Únete a la bibranche.
Unisciti alla bibranche.
So, hello everybody, and today I am pleased to have Jerald Yoo to have a speak about wearable eHealth from electrodes to signal processing. Jerald Yoo is a professor that comes from the National University of Singapore, and I hope.
Okay, looks like there's a system glitch.
Totally. Sorry, I just came back, and I hope you will enjoy his talk. So, Jerald, I'll let you introduce yourself. Sorry. Introduce yourself
no problem.
and start your talk.
Okay, thank you. Could you please put my slides on the screen?
Yeah, sure.
Yeah.
Yep.
Okay, hello everyone. Welcome and nice meeting you. My name is Jerald Yoo. I'm a professor at National University of Singapore. And today I'll be talking about the wearable eHealth from electrodes to signal processing. So this will be covering all the way from the electrode that touching your skin to the healthcare system that will having the signal processing aspect. Okay, so let's start. Before I start, I would like to ask you here, can anyone recognize what this photo is? Please make a guess. This is actually a neonatal ICU for the infants having some issues. As you can see, the infant will be typically hooked up in wires in the screen, as you can see. And noting the newborn heart rate is around 120 to 160 beats per minute, which translates to around 7 to 9K bits per hour. But if you look at it, only about currently 1 to 2% of the data that we collect with all this wire dangling are used, and the rest will be discarded. And typical NICU, neonatal ICU system records holds about 3 days worth of data. So what is the consequence of this? Is that the consequence is that we are killing babies. The newborns, neonatal mortality worldwide, as you can see, is quite high. It stands around 17 worldwide as of 2018. And even the developed countries, we have a significant portion. We cannot ignore these neonatal mortality per 1,000 live birth. Now, this translates to around 4 million infant mortality per year. That's also very significant numbers. Can we do something about it? Well, that's also linked to this graph that I would like to show you today, which is the glucose level of a patient suffering from diabetes type 2. So the blue line over here tells you the normal band for this patient, for the person to be considered as normal. But if you monitor this person from point A or point B, this person will be considered as normal. But as you can see from this graph, that's absolutely not the case. And this is why the NIH, the National Institute of Health in the US, has proposed the 4 Ps of medicine some time ago, which means the predictive, personalized, preemptive, and participatory for the healthcare. And that means we can enable the continuous health monitoring. We call it wearable eHealth, which is very, very necessary. Now, a good example of chronic conditions that can benefit from eHealth, especially the wearable eHealth, is seizure and epilepsy. So that's why I'm introducing this slide here. The prevalence of epilepsy is around 2 million in the US, and that's around 70 million in the worldwide. And this prevalence is higher in developing countries and in children group, which is very bad. But if you look at how we track the seizure, as of today, we are in 2021, is amazingly we still rely on mostly interviewing the patient. The physician is sitting with the patient and asking questions. For example, how many seizures did you have for the last 2 weeks? And that's based on that, the medication will be given. Of course, we also have in-hospital EEG monitoring accompanied by the video recording to confirm the cases. But the problem is that this doesn't work well with the like newborn babies or 2 or 3-year-old kids. But a lot of chronic conditions actually, the earlier you detect and treat, the better prognosis you'll have. So that means there's a clear discrepancy. You want to detect early as possible, but in case of seizure and epilepsy and a lot of chronic conditions that you rely on interviewing the patient, that doesn't work for the kids. So how do we fill up this gap? That's the good question. And one of the answer, although it's not the only answer, is the wearable e-healthcare. And that's enabled by having patch form factors or wearable electronics that does the healthcare continuously. And also very importantly is pervasively. And what does that mean is that it'll be always on body and flexible platform is very good, very, very, very needed because you don't want this patient to disconnect and stop using it. And in order to be very flexible, you also need to think about what the form factor you're going to design. And here I list the 3 characteristics of this eHealth, which is disposable, easy to use, and convenient. Okay, so in the sensor side, we also talk about this hospital setting machines, which we only care about the biopotential high fidelity signal acquisition. And you don't need to actually worry about feature extraction or classification or recording or stimulation for this hospital setup. But if you want to move towards the eHealth and wearables, you definitely want to add a feature extraction and classification so that it can be patient specific. On top of that, if you want to close the loop, you better also integrate the stimulation aspect. So that's actually what we are going to talk about in today's talk for the feature extraction, classification, stimulation, as well as the signal acquisition side. Okay, but before we move forward, let me ask you one question here. High blood sugar, which we call it hyperglycemia, is an emergency situation for diabetic patients. Is this statement true or false? Can you make a guess? I ask you again. High blood sugar is an emergency situation for diabetic patients. Is this true or false? It sounds like a no-brainer, But let me give you the answer. Answer is no, that's not an emergency situation. Now, what do I mean by that? So we also have to think about when you design the eHealth, engineering aspect versus the clinical needs. So the diabetes, we to detect the true glucose level in the body, many technology was introduced, including the smart contact lens. Some people try to monitor the urine in your stool, I mean the toilet. And also recently, this is becoming more popular for ambulatory glucose tracking with the patch. Now, all of these are very effective in tracking glucose. However, there are two aspects. So there are two symptoms that the diabetic patient has to be aware of. One is the hyperglycemia, as I said, where the high blood sugar is becoming a problem. And there's another thing which is called hypoglycemia, and this is a low blood sugar. So unlike what we think and commonly think, hyperglycemia is a killing, it's a very lethal case, but it's not emergency. In other words, having 300 milligrams per deciliter doesn't kill you immediately. However, when the hypoglycemia, the low blood sugar is involved, if you don't attend right away within minutes, you are in trouble. You may fall into coma, and in some cases, it will lead to the death of a patient. So this is an emergency situation. But the smart contact lens, smart toilet, smart patch, they are not good at tracking hypoglycemia because the blue body fluid that they monitor glucose from, there's a delay, around typically 30 minutes to 1 hour delay before it shows up in the body fluid. So if your target is to track the hypoglycemia, obviously these smart contact lens and toilet and these approaches, you might need to think again. If you're thinking about tracking the glucose in everyday life for 24/7, not necessarily the hypoglycemia, then the contact lens is good. So again, you have to think about what is your ultimate need in the application level. In other words, the system level consideration at the application perspective is very, very important. Okay, with that in mind, I split my talk into four topics. I'll be spending around 10 minutes to 15 minutes for each. First is the platform. This is a wearable eHealth. How do you make it wearable? I introduced the fabric or polymer circuit board. Second is the sensor interface circuit, because a flexible platform actually doesn't go along with electronics that well. So electronics has to do the diligence. Third is the digital backend, where you can think about how to classify the symptom of a patient. So that's after you have composed your patch with the sensor interface that can cope with the platform. And then you're going to have a processing that will actually detect the symptom of a patient. And I'll give an example of the seizure detection system. All right, so let's look at the platform first. So you can start off with the flexible electronics by making the existing PCB flexible, but I typically enjoy doing the other way around. Let's start from something that's already flexible. And what is naturally wearable? That's, I would say, textile, or sometimes the hydrocolloid gels. Or you can do the screen printing on the with the conductive ink on the fabric or polymer to integrate the electronics with the chip. You have everything on chip, and then you can integrate that onto that textile platform that is screen printed. And that's naturally wearable and aesthetically right. Of course, there are many, many difficulties in the electronic perspective, but let's put that aside at this point. And you can also fabricate the fabric electrode out of it, or polymer electrode as well. That's very wearable. The problem, however, is that you have the higher skin to electrode impedance, which will be a headache for the analog designers in the interface. And that higher skin to electrode interface impedance leads to higher noise as well as more stabilization time. So what do I mean by that? We fabricated the fabric circuit board based electrodes and then measured the impedance of the skin electrode impedance interface. And we find that after stabilization of around 10 minutes, you still have around an order of magnitude higher impedance when compared with the wet electrode. The wet electrode I'm referring to here is the 3M electrode that you can use. And that's bad because this means the loading effect will be eating up the signal strength, which is already very weak. So that means that the input impedance of the amplifier has to be fairly high. Now, if you look at the frequency response of this electrode, fortunately, that's very similar characteristic as that of the 3M electrode, but again, it has around 1 order of magnitude higher impedance. That doesn't change. So we have to cope with that. We can conclude the dry electrode with a similar form factor has the area of it requires around area of 2 square centimeters or higher, and it should be more suitable for monitoring over 20 minutes because of the stabilization time that you had initially. So for in-hospital monitoring, for let's say spontaneous monitoring, probably this is not a good choice. But if you're doing it for 3 days, 4 days of monitoring, probably the first 10 minutes is not a big issue. Okay, so then let's move on to the sensor interface circuit. We know that the platform with the textile has some issues with noise and then high electrode impedance, skin electrode impedance. Then how do you cope with that in the sensor interface? But before we jump into the circuit aspect, you need to also understand the biopotential aspect. If you look at the frequency bandwidth of the physiological signal we are interested in, such as ECG, EEG, or EMG, most of them fall below 1 kilohertz range. And that below 1 kilohertz, unfortunately, we have our friendly 1RF noise, which is inversely proportional frequency. And we also have an electro DC offset and our unavoidable friend, 50-60 hertz interference. That has to be dealt with. And this is more critical than you might think. We'll come back to that in the coming slides. If I were to list up all the challenges, first of all, in the interface of the biomedical, first of all, the signal itself is very small in the amplitude. So as you can see, the signal itself is already in the microvolt region for the EEG case, and ECG, each order of magnitude higher, but still it's very small. And you also have 1RF noise, drift with the CMLR problems, and the 50-60 hertz interference is something that we cannot avoid. Okay, so I mentioned about the 50-60 hertz noise, but how serious is that actually? So to test it, I did a very simple experiment here. This is myself in the video that I'll be showing you. And I'm driving the electrode that is with the floating ground here. So I'm only having the signal electrode, probe of the signal portion of the probe. And I can see that there's around 7-volt peak to peak of nice sine wave coupling to my body. And where does that 7-volt peak to peak coming from? It's actually coming from the power line from it's omnipresent, right? In the building, there's a light system, there's electronics, appliances nearby that couples your body. And because the signal that we are trying to amplify is in the millivolt or in the microvolt region, this common mode of 7-volt peak to peak or even higher is a big problem. So to cope with that, we have dynamic offset cancellation techniques. We call it dynamic offset cancellation because you can cancel out some dynamic offset, including the 1RF noise. And in biomedical, we typically there are 2 ways, largely speaking, there are 2 popular ways to deal with the this one dynamic offset. One is the auto-zeroing, the other one is chopping. But we typically use chopping for biomedical because it's inherently differential. So let me tell you what that means. Some of you are already familiar with it, but just to do a recap. So you have the signal to start off with, and you're going to up modulate it just like in the AM modulation. This is the frequency domain signal you're going to see. And after that, you can see that amplifier will be adding some noise, 1RF noise, such as low frequency noises. And after you demodulate, just like AM demodulation, now you can see that noise portion is up modulated into higher frequency range. And then you have the signal. One component goes to DC again, the baseband, and the other one goes to twice the chopping frequency. And of course, with the nice low pass filter, you can recover the amplified version of the nice signal. So that's what the chopping does in the frequency domain. Now, One issue with the chopping is that it'll degrade the input impedance. For example, let's look at this case. You can mitigate the dynamic offset and the amplifiers, as well as the input capacitors mismatch, that's a static offset, that can be also mitigated by chopping. It's a chopper switch over here, which is swapping the plus and minus signal in the input side. But by doing so, you're actually getting a good dynamic offset cancellation. At the same time, you have the limited input impedance because you have the differential capacitors. Chopper in front of the capacitors, the input impedance will degrade considerably. And that's a bad news for the wearable interface. Why? Because as I said, especially if you're talking about dry electrode, the skin to electrode impedance is high. And if you have a low input impedance in the amplifier, the signal with the loading effect will be all killed. So to improve that, people have tried many different technologies, and this is a good example. Some people try to chop it in the virtual ground of the amplifier, which in fact effectively boosts up the input impedance. And in this particular case, the impedance was boosted to around 700 mega ohms. That's very, very good. But you can see that by doing so, the input capacitors are before the chopper, which means the mismatch of these capacitors will be reflected into the offset, and that means the CMLR will be degraded. That's a bad news. So the other way to improve the input impedance is to have a positive feedback loop in the impedance boosting loop, in the form of the impedance boosting loop. The way it works is that, let's say if your input signal has current flowing in an X amount, then you can provide 9x positive feedback. So effectively, the current fed into the amplifier will be 10x, although the actual current drawn from the signal electrode is only X. So effectively, you're boosting up the frequency, you're boosting up the impedance. And that's quite a smart way to improve the efficiency, improve the impedance of the amplifier. And you can also deal with the chopper-induced ripples. I didn't mention it very briefly, but by doing the chopping, which is swapping between channels, there will be always rippling happening in the signal path, and that can be mitigated by having a negative feedback through the chopper ripple reduction loop. That's what these people say. You can also integrate the ripple reduction loop with the impedance boosting loop, and then also the DC server loop to improve the DC server loop to mitigate the DC offset in the electrode. And that can be all integrated together, which gives a good response in the biopotential amplifiers. But even so, this is not enough to suppress the high CMLR, high common mode interference I already showed you in the video. So how do you deal with the common mode interference? There are many ways doing it, but one way of handling that is to have this common mode interference suppression technique. And the core is as follows. This technique, let's say that you're trying to amplify the EEG signal. You can have the large common mode interference that you have already seen in the video. And then you can average that out from the common mode averaging unit, and then let that common mode signal ride on the circuit's VDD and ground. So it's simultaneously driving the VDD and ground with the common mode interference. So what's going to happen is the delta of the VDD to ground, which is the circuit's perspective, the supply voltage, will remain constant. Although there's a common mode interference coming in, because the supply and the ground is swinging at the same time, riding on the common mode interference, effectively you're not seeing that. That can actually cancel out around 50 volts peak-to-peak common mode interference. That's quite effective. Now, let's look at how effective that technique will be. Okay, so here, I have a laptop. Especially these days, we have many laptops with the aluminum casing, and these are particularly a big source of common mode interference. You'll see it immediately in the screen. Now, what we are doing here is that we have on the left side the commercial amplifier. Left side is our amplifier with the common mode suppression, and right side in the screen is the commercial amplifier. And then the moment you touch the you touch the laptop, which is connected to the AC supply, you can see that the commercial one, which also has a good common mode rejection ratio, but that's not sufficient. The moment you touch the laptop's out casing, the common mode interference that comes into your body is saturate the amplifier. Whereas if you have the common mode suppression that I explained before, to have the VDD and ground riding on that, you can see that the ECG is still coming normally. So, and we call it instantaneous common mode interference because it just may happen when you touch the like appliances or your laptop, or you go nearby the interference source, which happens all the time in the indoor environment. Right? You don't want that in the eHealth patch to stop working when you touch the laptop. So this is why we need to care about the common mode interference a lot. Okay, another thing to think about is the multi-channel aspect. So if you think about single channel, or let's say a couple of channels, probably you don't need to worry about area or the power consumption too much. But let's say you're talking about seizure detection with, let's say, 20 or 30 channels to deal with. Then the power consumption of these multi-channels as well as the on-chip area becomes an issue. So how can you make multi-channel amplifiers? Well, a brute force type of way is to have multiple channels composed by multiple amplifiers. So you can see that you have multiple, let's say if you need 10 channels, integrate 10 amplifiers. That's obviously scalably increasing the power consumption as well as the chip area. So people have been thinking, can we share several amplifiers or even single amplifiers among multiple channels? Then you can save the power consumption as well as the area consumption, especially when the channel becomes really large number. Well, that sounds interesting. So let's see how we can do that. One way of doing it, to start off with, is the conventional way to have multiple channel with multiple amplifiers. We call it brute force type of amplifiers, where obviously, as I said, the power consumption will increase too much and area overhead as much as well. But there was also a very smart way of achieving single amplifier amplifying multiple channels. We call it orthogonal frequency chopping, or OFC. So what they do is that you can chop different channels, use different frequency for chopping. And that different frequency can be multiple of the base frequency. And as you already know, by doing the multiples, the odd numbers of multiples will be suppressed out. So that means you can use the channel 1 uses 1 FC, channel 2 uses 2 FCs, channel 3 uses 3 FC, and etc. And that will scalably, that has to be 3 FC, 3 FC is the harmonics. But if you use the multiples, for example, 2 FC and then 2 square of FC, you can see that it doesn't fall into the harmonics. So this is why if you have n channels, you can effectively have 2 to the power of n multiplied by the frequency of the base frequency chopping. You need a wider bandwidth, but nevertheless, you can multiply the channels you can amplify the multiple channel with a single amplifier. That's fascinating. The only overhead here will be the power overhead because of the increased bandwidth. But if you increase the number of channels, 2 to the power of n, that means it's exponential increase in the bandwidth. That's one limitation we have. So how can you overcome that? Well, what we can do is that instead of using a single tone clock in chopping, why don't we use the orthogonal, like a wash code type of chopping? So what it means is that instead of using 1010 all the time, you can use the orthogonal code and then multiply, you're gonna chop it with different channels. In other words, channel 1 and channel 2 have orthogonality, just like a CDMA approach. And by doing so, you don't have to increase the bandwidth that much. Means that you now have, instead of exponential increase in the bandwidth, you only have linear increase in the bandwidth, as you can see. Right? That's interesting. And if you compare with the orthogonal frequency chopping versus the orthogonal code chopping is using the orthogonal code for the chopper clock. You can see that the area saving is around 70% or 64% compared with the conventional chopping, and it's around half of that of the, 30% less than that of the OFC. Whereas the power consumption, if you compare with the conventional chopping for 15 channels, you will see that the power consumption reduction is considerably higher. It's around 99% reduction in power saving. So just to summarize the multi-channel aspect, which is essential for the wearables, eHealth, for a couple of channels, you can just go ahead with multiple amplifiers doing multiple channels. For, let's say, 4 to 6 channels, probably you can use the exponential, at the cost of exponential increase in the bandwidth, you can go for orthogonal frequency chopping. But let's say for 10 channels and above, you might want to use the orthogonal code chopping to save the area and power consumption at the same time. And that summarizes my talk on the wearable IA side, which is the second topic of the talk out of 4. So you can use the capacitive gain element for the capacitive coupled amplifiers to enable the rail-to-rail DC headroom, but at the cost of a limited CMLR and noise problem. So to come up with mitigation of the noise, especially dynamic offset, you can apply the chopper stabilization IAs, which is quite popular these days. And you can also mitigate the issues that is induced by the chopper by having the impedance boosting loop, because if you have the input choppers at the input side, the input impedance of the amplifier drops. So to mitigate that, you can add the impedance boosting loop. And that is quite important for the dry electrode case, especially because of the high skin electrode impedance. And you can also add the ripple reduction loop, and not to mention the common mode interference, especially for wearable environment for ambulatory. It's very, very important. And if you want to form a multi-channel IAs, you can also think about having orthogonal code chopping so that you can you don't have to worry too much about power scaling up too much or the area consumption too much. Okay, so now let's move on to the digital backend. So now you have formed a wearable patch with the fabric or the polymer, and then you also design an amplifier that copes with the wearable environment problem, which is the noise and dynamic offset. And then now you have high fidelity signal. So now it's time for you to do the processing in the digital backend to classify the symptom. So let's come back to the seizure example that I mentioned before. So you might think seizure, when a patient is struck with the seizure, the EEG become probably noisier than normal case. So then maybe you can do the filtering and have a threshold-based detection will be sufficient. But unfortunately, that's not the case, especially for surface EEG. So there are 2 types. The intracranial EEG, which is implantable, I mean the surface of the brain. That stereotype somewhat fits well. So when the seizure strikes, it becomes the energy becomes much higher compared with the normal pattern. But for the surface EEG, that's not the case. So let's look at this patient A in the left. When the seizure strikes, you can see that the EEG actually becomes noisier. But what about the patient in the right? When the seizure strikes, compared with the normal case, the EEG pattern becomes quieter. So how can one hardware detect both cases? That's very challenging. We call it patient-to-patient variations. I hope that's the only case, but that's actually not. Even with the same patient, as the patient ages, the pattern may change. Right? That's another headache for the hardware designers. And lastly, there are also different types of seizure. One type of seizure, we call it focal seizure, where you can detect from one part of your skull, whereas some cases, it's a generalized case, you can monitor this pattern for all over your skull. So each patient has different pattern. Even one patient has different pattern over time. So this means we have to learn these patterns for each patient. We call it patient-specific detection. All right, this sounds easy, but it's actually not. Now, let me summarize the challenges that we have to overcome when you do the patient-specific seizure detection. First of all, you need to have energy efficiency in the system aspect because you need to have at least 3 to 5 days of monitoring to cope with the wearable eHealth. The form factor has to be as small as possible and it has to be pervasive. Otherwise, patient may not be using it in everyday life. And the latency for the seizure detection, you also have to always record the raw data for clinician to survey that. And you must detect the seizure prior to clinical onset. Typically, depending on some patients, there may be around 10 seconds to 30-second latency before the clinical onset strikes. There's already an electrical onset from the trace. So you need to detect that electrical onset prior to clinical onset. So that's why there's 2-second latency rule comes in. And most importantly, you only have limited number of training sets. This is very, very different from image classification, where you have a lot of image sets to train with. For a different patient, if you're lucky, you have only about 1 or 2 training sets to deal with. So that's really challenging. So let me tell you why. You might think, okay, so if you want to learn about patient's pattern, let's use the AI, or let's use the deep learning. But unfortunately, that doesn't work that way. So let me first define my terminology here. In the world of the artificial intelligence, AI, machine learning is a subset. In a machine learning, there are some traditional machine learning such as SVM, decision trees, nearest neighbor, linear regression, and etc. And there's also neural network based such as the CNN, DNN, RNN, and etc. Now, if you look at the applications in terms of the applications and also in the y-axis, the latency versus the available training set in the x-axis, the big data analysis such as the medical image analysis is a classical example where the DNN is a perfect fit. You have a lot of training sets to deal with, and the latency is not a big issue. The self-driving car, on the contrary, does care about the latency. You definitely need to have less than 30 milliseconds for the latency, and the power consumption is not a big issue here. But you also have a lot of training data. So, for example, Google's Waymo, you know that it has been running for years, collecting sufficient data. Now, that's also perfect for deep learning. The wearable eHealthcare for patient-specific eHealthcare. First of all, you don't have that tons of power budget to deal with. And more importantly, you need to have 2 seconds of latency. But more importantly, you only have a handful of training sets, let's say 1 or 2 training sets. And with that, deep learning is not a good fit. So you might have to think about traditional machine learning instead. So just to recap again, there are 2 types of seizure detection. One is the real-time onset detection that we are talking about with the less than 2-second latency with good accuracy and typically used for closed loop system. That's for machine learning, typical machine learning. And there's also equally important aspect, which is the seizure prediction and post-analysis. You don't have to worry too much about the latency here. And here the goal is to have highest possible accuracy. You don't have to have a patient-specific detection here. So in this case, DNN is the way to go. But in this talk, we are focusing on the patient-specific closed-loop system. Hence, we have to go for machine learning instead. So how do you do that? Well, you can have the 3 types of information. First is a spectral information. You can split the band. Typically, we use up to 30 hertz out of the 200 hertz EEG bandwidth because most of the seizure information lies within the first 30 hertz. And then you can have the multiple channel information as well as 2-second. There's a temporal information. So the feature vector will be called as a spectral information, spatial information, and temporal information. That's one vector. And then you're going to lie it in the domain feature in the domain here. And then you're going to classify with the SVM is one example, but let's say you can classify whether it's a seizure or not. Right? With the linear SVM, we can see that around 85% sensitivity is achieved, and a specificity with the false positive rate is around 5% on average. So the detection rate in the sensitivity wise is okay, but the false positive is relatively too high with the linear classifier. So we can use the nonlinear SVM, which actually carves away this classification boundary better. And by doing so, the false positive rate is significantly reduced. Now the specificity is around 99.2%, which is okay. and the sensitivity is around 95%, which is also very good. Okay, so if you look at here up to this point, we may think, oh, it looks like nonlinear SVM is the way to go. But there's also a missing information. This is that nonlinear SVM works well if you had sufficient training sets. So if you have a database in priori with such as MIT CHP database, yes, it works well because you can have sufficient training sets. But in the real seizure patients, as I said, at best you have one or two seizure patterns to train this pattern. Then this nonlinear SVM may not work well. In some cases, in most of the cases, actually it works worse with the less limited training sets. So then we can come up with other ideas. Okay, then let's use two LSVM, linear SVMs, but train one for the sensitivity. You don't care about the specificity for one classifier. And then also train one classifier just for the specificity. You don't care too much about the sensitivity. And can we merge that information? Well, that's actually I say a simple way to solve this issue, but it's actually fairly powerful. With doing that, we can see that one classifier is used for the sensitivity, the other classifier used for the specificity. And then you can use the weight and average block to use the arbiter to determine whether it is actual seizure or not. That can catch the two birds with one stone, the sensitivity and specificity here. And if you compare with the single LSVM case, you can see that the sensitivity is around 95%, which is good. And specificity has significantly improved, 98% versus 95.5%. Well, I'll say the specificity should be better, could be better. It should be targeted, let's say 99% or even higher for the specificity wise. But I would say compared with the 95%, it's much better. Okay, so that goes to the last section of the talk today. So we will integrate everything together, the patch, the sensor interface circuit, and digital backend to a system. So there are multiple versions of this seizure detection SoC, but I'm just showing one example here, where you have the amplifier that amplifies multiple channels with a single amplifier. And then you have this two SVM classifier, non-linear SVM, one trained for the sensitivity, the other one trained for the specificity. And then you can also have the patient-specific stimulation pattern given that closes the loop. And for the interest of time, I'm not going to details about the stimulation with the patient-specific stimulations, but you can also refer to the PhilSci Symposium 2021 paper, this year's paper, for the online tuning as well as patient-specific stimulation. Okay, for the transcranial electric stimulation, you have three types. One is the charge-based, the other one is the voltage-based. The third one is the charge-based, and the first one is the current-based. The best efficacy comes from the either charge-based stimulation or the current stimulation, but that comes at the cost, which is the high power consumption. So for low power, you might want to just go the voltage mode stimulation. But that means if you apply the constant voltage in the stimulation pulse, that means depending on the skin electrode impedance, the current that is injected to the body will be changing. And you have to balance that out. So this means you have to carefully monitor the skin to electrode impedance. How do you do that? Well, typically people will have been using a sine wave injection into your body and then measure the voltage fluctuation to cope with the impedance variations. But that comes at the higher power consumption. And as I said, in the wearable eHealth, you want to save the power consumption. We also can do the following. So because you're going to have the stimulation pulse in the voltage mode injected anyway, that variation in the skin electrode impedance will be reflected in the RC time constant. So this is how you're going to monitor this slew rate of the pulse that you're applying for the stimulation. If you monitor that, you can actually induce the relative skin electrode impedance aspect, and then you can cope with it. That's low power enough. Okay, so let's look at how this fits together. So that system that we presented, we also tested with the database from the MIT CHB. And this top is showing the seizure marked by the expert, and below is the classification result from the classifier in the full SOC. You can see there are some false positives, but this is fairly good enough in detection. But this one actually, even with your naked eye, can detect fairly well. And so is the patient 5. You don't even need a complicated system. You can immediately detect this is a seizure even with the naked eye. But let's look at the patient 15. By just looking into the EEG pattern, it's almost impossible to detect this is a seizure, but the SOC actually successfully classifies well. Patient 11, it's a bit vague. You have some false positive here, but I'll say it's good enough. Patient 12 as well. And you can also note that detection is slightly ahead of the actual pattern showing up. Patient 6, this has been traditionally a headache case for many cases. This is a female of age of 1.5 years. And typically, the earlier the patient is, the harder it gets to detect because there are multiple patterns to deal with. And you can see that this SOC has detected the seizure well, but the problem is the other time, the half of time, you have false positive. So to cope with that, we also finally solved this issue and presented in this year's paper. The trick is to do the time averaging and channel averaging on the multiple channels, and we can actually solve this issue and cope with the, we also do the online tuning to cope with patient variations so that can solve the issue. Patient 22 is no exception here. Then we also have the local hospital patient, which if you look at the time scale is different from the previous slide. You can see that around 3 to 4 seconds before the actual marking, which is eminent by the video footage, you can see that this pattern was well detected from the system. And different seizure, you can see that from the EEG, it's very difficult to detect, but nevertheless, the system is always detecting it well. Right, this is another pattern. Again, you can see that in the raw EEG, it's very difficult to see, but the SOC successfully detects. The sensitivity was around 96%. The specificity is around 98.1. Again, the specificity can be better, but I'll say this is acceptable. Okay, so let me conclude my talk. For the wearable eHealth, the system level consideration is required. It's not only about highest performing IA or having the best electrode or best classifier, but putting them together is very, very important. We shouldn't forget what our ultimate goal is. In wearable eHealth, the ultimate goal will be conveniently, with the convenience, can we detect with the long term the chronic conditions or monitor this patient condition well. And that is enabled by having the trade-off between the specification, between the analog front end, digital back end, as well as the platform, and system integration aspect as well. And wearable e-healthcare is enabling the proactive healthcare, which gives the dry electrodes to long-term monitoring with the safety and reliability aspect considered. And last but not least, machine learning, not necessarily deep learning, but machine learning as a whole is good fit for the personalized healthcare. And you need to also think about choosing the right classifier for the application of your need. And detection of epileptic seizure, for example, was possible with the electrical onset detection prior to clinical onset from the surface EEG. Okay, so that concludes my talk. Thank you for your attention. If you have any questions, please let me know.
Okay, so I would like first to thank you for the talk. It was very interesting. Now we will go for a Q&A session. So in the chat, don't hesitate to ask your question. I will directly ask to the professor. But personally, I was pretty much interested in the talk. I have a personal question.
Yes.
So first, I would like to know, Do you think energy efficiency and size of the wearable devices can be associated with the development of intelligent device? I mean, you talk about adding machine learning in those devices, but can they be compatible even though the device will be more energy will consume more energy, and can they take the same size? Can they take the same size?
That's right. So I think that's an excellent question. So if I rephrase your question, you are saying by adding this functionality of seizure detection, or let's say classification and then signal processing into this already energy constrained system, wouldn't that impact the efficiency, like let's say battery lifetime, right?
Yeah.
So actually, absolutely it does. So that's why we have to have the SoC with the signal processing instead of having, okay, let's see if I can go to the slide that I think I included one. Sorry, I will be sharing once again.
Yeah, don't worry.
Okay, never mind. So in a nutshell, what we need to do is that the signal processing aspect should be on the on-chip instead of off-chip. Let's say if you want to do it from the smartphone, or let's say your mobile device, you need to stream this raw data
Yeah.
instead of doing the on-chip. Because at first you might think that if you stream the data, you don't do the signal processing on-chip, the energy efficiency will be higher because you don't have to have the machine learning on-chip. But you also need to think about the radio power. Typically, the radio, even if it's Bluetooth, so to speak, we say low power, which is radio. But Bluetooth, compared with the on-chip signal processing, is orders of magnitude consuming higher power. So that's why you might want to integrate the on-chip machine learning. So to answer your question, yes, it impacts the energy efficiency, but compared with compressing the raw data and then shooting over the radio, that's much more efficient. So I think there's a trade-off again, clearly. But that's an
Yeah,
excellent
and
question. Yeah.
adding for this, it was a bit in your conclusion to choose a good trade-off, considering the needs in the device you are developing. I have another question this time from the chat, from Prasad Kumar, which comes University Polytechnical University of Catalunya in Barcelona. He asked, what is efficient rate of seizure detection using smartwatches?
Yeah. So this is also a good question. So if I understand correctly, the question is how efficient or how effective it is to detect a seizure with the smartwatches. So um, if you're talking about epilepsy detection, so epilepsy is defined as recurrent seizures, right? Um, there are some wearables that detect the epilepsy. So in other words, when the patient has the clinical onset, the smartwatch can even detect the epilepsy. Whereas if you're talking about seizure is currently the best way to detect is through the surface EEG or through the IEEG. So because this clinical onset hasn't occurred yet when the electrical onset is there. So if you're talking about the seizure in the EEG pattern, properly smartwatch is not the best way to go. But if you're targeting detection of the epilepsy, the smartwatch can be an effective means to track and record the epileptic seizure occurrences. So there are different needs, right? If your target is to close the loop with the stimulation, you obviously want to trigger the stimulation prior to clinical onset. In that case, smartwatch is not effective way. However, if your goal is to detect the epileptic seizure as a whole, probably smartwatch is also effective way. So again, there's no ultimate solution. I think it depends on what is the application goal you're looking for. But that was an excellent question.
So thank you for answering this question. I don't know if Erwan has another question, but it doesn't look like a question, so I'm not sure to ask you. But I would like to thank you for this talk.
Thank you.
It was only 2 questions, but I think your presentation answered a lot of our question on wearable eHealth devices. And I hope for all the students that are participating in the summer school, in the IoT summer school in Bordeaux, were interested in this talk to help them to consider and to think about maybe the future device you will design. So again, Jerald, Professor Jerald, thank you, and I would like
thank you.
to say to all the viewers to have a good evening.
Yes, and
Thank
I
you.
see that. Thank you so much for the invitation, as well as if you have further questions, please feel free to drop me an email. I'll be happy to answer the question. My email is shown here. Thank you. And enjoy the rest of the conference. Thank you.
Yeah.
Bye.
So don't forget to write the email.
Thank
So
you.
goodbye everyone, and thank you again.
Thank you. Yeah.